Well, hello, ladies and gentlemen. So let's finish off vapor power cycles here, the Rankine cycle. So we did a fairly in-depth example. Took a little bit of time last time to go through and do a fairly in-depth example. So let's finish up the Rankine cycle by talking about strategies for improving performance of the Rankine cycle. Remember, we talked about strategies for improving the performance of the Brayton cycle. So what we had multi-stage compression and expansion, along with reheat, intercooling, and then we had regeneration as well. All those strategies could be used to improve the efficiency or output power of a Brayton cycle. We'll talk a little bit about the equivalent of regeneration for a Rankine cycle. In particular, it's called feed heating. We're going to talk about feed heating, which is a method of implementing regeneration in a Rankine cycle. Try to recover some of the heat that would have been lost, rejected in the condenser. Try to recover some of that heat, put it back in before it gets lost through the condenser. So do a little bit of regeneration if possible, okay? And then we're going to move on to something completely different. We're going to move on to vapor compression refrigeration devices. So we're going to try to build a device that runs in the opposite direction as, for example, a Rankine cycle. We're going to try to reverse a Rankine cycle. A Rankine cycle is irreversible internally and externally, but we can try to envision a device that operates in the reverse direction. And we're going to use that to develop what's called the ideal vapor compression refrigeration cycle. And then we'll talk about the effects of irreversibility in the cycle. And then we'll start and see if we can get through an example on non-ideal vapor compression refrigeration. Okay, that's the plan for today. Okay, so let me put up a TS diagram for our, let's say, for an ideal Rankine cycle. So, so we have the ideal Rankine cycle. How about with superheat? How about with superheat? Just to make the TS diagram a little bit more legible, a little bit larger, okay? So we have TS. So here's our saturation dome. So we start off with a saturated liquid at state 1. Oh, I'm sorry. Let me put in the isobars here, the P min and the P max, or if you like, the P condenser and the P boiler. So P min is the condenser, and P max is the boiler pressure. So P max equals P boiler. So we start off with a saturated liquid, and then we isentropically compress, very small temperature change. It looks a little bit bigger than it does in real life here. Very small temperature change, but we go up to the Pmax isobar through a reversible pump. And then ideal cycle, we have constant pressure heat addition in the boiler up to some sort of a superheated state at state 3. So this is our Q boiler. And then presumably we have a isentropic, because it's reversible and adiabatic, ideal expansion of turbine. No heat transfer in the pump, no heat transfer in the turbine. And then we have heat rejection in the condenser. Now, if you recall from the Brayton cycle, the idea of regeneration was to take some of the heat that would have been rejected to the atmosphere and take it back and preheat the air before it went into the combustor. The idea is kind of similar here. It's not quite as effective, but it can be somewhat effective. The idea is to take some of the energy or heat, intercept some of the energy in the flow somewhere during the expansion process in the turbine, and feed it back feed it back during the compression process. So the idea is to take some heat, Q bleed. Let's bleed away some heat, some energy from the high temperature side and funnel it back to the low temperature side in the hope that we can improve the efficiency of our Rankine cycle. Okay, so that's the idea. It's similar to the idea of regeneration in a regenerator for Brayton cycle. Similar idea here, similar idea. So let me show you how that's implemented in the Rankine cycle. So here we have a Rankine cycle with multi-stage compression and multi-stage expansion. So what we have here is a condenser. We start off outside, just downstream of the condenser, as a saturated liquid as usual. And instead of having a single pump, we have two pumps. A low pressure pump, LPP, a high pressure pump, HPP, and in between we have this thing called a open water feed heater, OWFH, open water feed heater. So how does this feed heater work? Well, let me explain the rest of the cycle here. So we have this open water feed heater, which we'll talk about in a moment. Remember, we start off as a saturated liquid at the low pressure pump intake. So we partially compress the liquid water. We pass the liquid water through this feed heater here, and we'll talk about exactly what it does in a moment. And then we complete the compression process all the way up to the boiler pressure by passing the water through a high pressure pump. Then heat gets added in the boiler. So we have our Q dot boiler here. We partially expand the superheated vapor. Presumably it comes out of the boiler as a superheated vapor in a high pressure turbine. We bleed off, so once we get through the high pressure turbine, we bleed off a small amount of mass flow, just a little bit of the mass flow, and it gets sent into this open water feed heater, okay? And it mixes with the low pressure pump outlet liquid water. And then we proceed to expand the remaining, what's left over of the mass flow, in a low pressure turbine, and then that gets sent to the condenser and we reject the heat in the condenser, Q dot condenser. So let's talk about what this open water feed heating does here. Let's go to the TS diagram. So we have here state one. So we have state one here, which as usual is a saturated liquid into the low pressure pump. Saturated liquid into the low pressure pump. Now we pump up the flow that goes through the low pressure pump up to state two. And state two is some intermediate pressure. So here's your condenser pressure. So here's your P1 isobar, which is your condenser pressure. We have an intermediate state pressure, which is P2 and P6, by the way. We have mixing, if you like, isobaric mixing in this feed heater. So P2 and P6 are the same. So we have compression up to the intermediate pressure at state two. Now, that is going to be some kind of a supercooled liquid. The higher the efficiency of the low pressure pump, the more supercooled this liquid is going to be. So state two is not on the dome, it's away from the dome in the supercooled liquid region. Now we're going to bleed off just enough steam, intermediate pressure, superheated vapor steam. We're going to bleed off just enough to heat up the liquid water to a saturated liquid at the intermediate pressure. So on the TS diagram, we're going to take a jump from supercooled liquid at the intermediate pressure to saturated liquid at the intermediate pressure. So we're bleeding off a certain amount of H2O. from the exit of the high pressure turbine. We're going to bleed off a certain amount. We're going to mix it with supercooled liquid, which comes from the low pressure pump outlet. We're going to mix it isobarically in this open water feed heater. And that's going to push us up to state 3. It's going to heat up the H2O at state 3 to a saturated liquid. So we're going to take high energy steam, low energy, or low enthalpy if you like, supercooled liquid, and we're going to heat it up to a saturated liquid. So we're going to increase the enthalpy of the flow going into our high pressure pump. So we end up with a saturated liquid at state 3 going into the high pressure pump. The exit of the high pressure pump, we're at the boiler pressure. We add the heat in the boiler. We end up, let's say, at a superheated vapor going into the high pressure turbine. That's state 5. Superheated vapor. Then we expand in the high pressure turbine down to the intermediate pressure. Notice there's an increase in entropy here. The high pressure turbine presumably is irreversible. So are the pumps. All the turbines and pumps I'm drawing here are irreversible. And then again, we bleed off some of this superheated vapor at the intermediate pressure. We bleed it off and use it to heat up or preheat the high pressure pump intake. And then we expand the remaining H2O down to the condenser pressure in the low pressure turbine. So you can kind of think of this. Again, let's go back to the picture we have here. You can kind of think of this as taking energy from the hot side of the cycle, funneling it into the low side of the cycle in the hope that we can regenerate or reuse some of that energy that would have been lost, or a proportion of it would have been lost in the condenser. So that's what this feed heating is all about, taking mass flow, or at least energy from the hot side of the cycle, taking that energy, or some of the energy, recycling it in the low temperature side of the cycle in the hope of reducing the amount of total heat rejected in the condenser. Okay? Now, open water feed heating is not as amazingly successful as regeneration in the Brayton cycle. The Brayton cycle example that we did previously, a lot of the heat rejected in the atmosphere could be reharvested or regenerated, and we had a significant, if you go back and look at the example with regeneration in the Brayton cycle, we had a significant increase in efficiency of the cycle. As I recall, without regeneration, the Brayton cycle example that we just did, thermal efficiency was about 25%, and I think with regeneration, with a regenerator efficiency of about 80%, as I recall, with regeneration, the thermal efficiency of the Brayton power plant gas turbine went up to like 46%. With these open water feed heaters here, you're lucky to get a 1, 2, maybe a 3% increase in efficiency of your overall Rankine cycle. But these Rankine cycles are used in power plants. There's a Rankine cycle right over there in the Blacksburg power plant. It's got turbines, it's got pumps, it's got a boiler, it's got condensers, all that steam coming out you see every day coming out. That's due to heat rejection at the condenser. And of course, it uses natural gas, coal, or maybe even a little bit of oil to run the boilers. So that thing's generating a lot of electricity. It's consuming a lot of fuel. If you can add an open water feed heater and boost efficiency by just a couple of %, that's a significant reduction in operating costs for the power plant. So power plants and, well, power plants on ships as well. So propulsion plants on ships, which often are operating off of a Rankine cycle, especially the old ships that were oil and coal fired, those have various open water feed heating systems as well, okay? So this open water feed heating gets you an extra % or 2 in efficiency of a Rankine cycle. Not as amazing improvement as with regeneration in the Brayton cycle that we looked at last time, okay? So I hope this gives you an idea of some ways to improve the efficiency of a Rankine cycle implementing various kinds of regeneration schemes. Open water feed heating is one of them. There's also closed water feed systems here, where you don't actually mix the bled H2O with the low pressure pump output H2O. You don't actually physically mix them. You simply have a heat exchanger in here. So these can therefore be at different pressures. This is an isobaric. Usually these open water feed heating systems are isobaric. Usually they're isobaric. Doesn't have to be isobaric. You could have a closed water feed heater with some kind of heat transfer going on in here where the fluids don't actually mix. But open water feed heating is probably the easiest to understand, okay? Okay, so for the last week and a half now, we've talked about, actually, wait, is it 2 weeks? 2 weeks, yeah. 2 weeks we've talked about power producing devices. We started off with closed system cycles. We looked at we again reminded ourselves about the Carnot cycle. We developed the Otto cycle, the Diesel cycle. We did an example involving an arbitrary closed system cycle. We calculated efficiencies, heat additions. Then we looked at open system cycles. We looked at the Brayton cycle, which is a gas turbine, uses air mixed with fuel burned to produce released heat in the combustor, and that heat is used to drive a turbine, which in turn is used to drive a compressor, and you hope to have some net power produced. Then we have H2O as a working fluid, not air, not an ideal gas. We have H2O. That's a power plant cycle, and that's a Rankine cycle we've been looking at for the last couple of days. Okay? So these are all power producing or work producing cycles. Let's shift gears here and let's look at work consuming devices, in other words, refrigerators and heat pumps. Let's investigate for a lecture or two the performance, and let's do an example involving a refrigeration or a heat pump device. We're going to look at closed systems, for example. We're going to look at closed systems that operate, we're going to look at an open system device that operates in a refrigeration cycle. That's the plan for the rest of today and a little bit of the next lecture. Look at refrigeration devices. So let's start with an ideal Rankine cycle here. So let's recall the ideal Rankine cycle with a pump, a compressor. So here's a saturation dome here. Here's our P-min, which is our condenser pressure. Here's our P-max, which is presumably our boiler pressure. Okay? And we started off as a saturated liquid, isentropically compress the working fluid up to the maximum pressure in some kind of a reversible pump. And then, of course, we add heat. So here, this is an ideal cycle. So we're adding heat here in the boiler, Q in the boiler. State 3 is a saturated vapor at the maximum pressure. This is the ideal Rankine cycle. And then, of course, we expand isentropically, reversibly, adiabatically expand the working fluid in a turbine. So there's no heat transfer going on here and no heat transfer going on in the pump. And then we reject the waste heat in the condenser. So Q out occurs from 4 to 1. Okay? And the cycle, of course, moves in the clockwise direction. So the cycle moves in the clockwise direction here. Okay? So this is the ideal Rankine cycle. In the examples that we've done superheated vapor for state 3. So we have superheat, and then we have non-ideal pumps and compressors. So these wouldn't be isentropic compression and expansion processes. So in the example that we did, okay? And of course, in real life, it's possible to have pressure changes as we go through the boiler or through the condenser, but we didn't deal with that. Now let's reverse this thing. Internally, this thing is reversible. Their isentropic efficiencies are 100% for the pump and turbine. So we could reverse this thing. So let's reverse ideal Rankin cycle. Let's reverse this thing. I'm just going to set everything backwards, including the heat transfers. So here's our dome. Here's our P min. And here's our P max. Okay? And so we start off again. Okay, so we're going to run this in reverse order. So let me make state 1 right here at the bottom. So instead of having expansion in the turbine, we now have compression in a compressor. Oops, that's not state 1. Yeah, it's somewhere inside the dome here. There's state 1. So we have compression in a compressor, not expansion in a turbine, all the way up to a saturated vapor at Pmax. So 1 to 2 is compression in a compressor. 1 to 2 compression in compressor. So our turbine, 3 to 4, became a compressor, 1 to 2. Then we have heat rejection, constant pressure at high pressure, down to state 3. So we have heat rejection output, Q out. I'm just reversing the direction of the Q in, and it becomes a Q out. So process 2 to 3 is isobaric heat rejection. By the way, we're starting off with a saturated vapor and we're going to a supercooled liquid. So we're condensing the working fluid. We're going from a vapor to a liquid, so we're condensing the fluid. So this is in a, quote, condenser, okay? In the condenser, the boiler became a condenser. That's nice. Then we have expansion in a reversed pump. The pump became a turbine? I don't know. Well, turbines deal with gases and vapors. Kind of odd to have a turbine that expands a liquid. Turbines don't do that. I'm just going to say reversed pump. So from 3 to 4, expansion in reversed pump. And then as we go from 4 to 1, instead of rejecting heat, we are adding heat. So Q in. So from 4 to 1, we have isobaric heat addition in, okay, wait a minute, in a what? What are we going to call this device that's receiving heat at the bottom end of our reverse cycle? We're going from a saturated liquid to a mixture of vapor and liquid. So we're boiling away or evaporating some of the saturated liquid. So I'm going to call this isobaric heating in an evaporator. It's like a fancy word for boiler. It's not really a boiler in the sense that it's not the high temperature end. It's an evaporator. It's actually on the low temperature end. Of course, when you boil fluid, you're adding heat to make it boil, so you're actually boiling at a low temperature. You're sucking up heat at a low temperature. It's going to make a cold place colder. You're condensing at a high temperature, going to make a hot place hotter. Heat pump, refrigerator. Heat pump, refrigerator. Okay? Depends on what Q you emphasize. Okay, so we have this reversed Rankine cycle, and it's working as a refrigerator. Clearly, we have to do work. We have to drive this compression process. We get a little bit of work back on this reverse pump process. In the previous example that we did, you recall how large the pump work was compared to the turbine work? It was extremely small. So the amount of work that we get back by expanding the fluid through this reverse pump is very small compared to the work required to drive the compressor. The compression process from 1 to 2. Okay? So this cycle is going in this direction. It's going counterclockwise, reverse direction of the Rankine cycle. Okay? Now, there are a couple of problems with this envisioned reversed ideal Rankine cycle. Just like there were some problems with the Rankine cycle. The big problem is that compressors do not like, just like turbines, compressors really don't like working with liquid in the fluid. Compressors like a gas to compress. If you mix droplets of condensed liquid into a gas being compressed, it's going to cause significant damage to the compressor. If you have way too much liquid, you're down here and you try to put this through a compressor, you will lock up or jam and break the compressor because liquids are incompressible. So having state 1 being a mixture is not so good for a compressor. It'd be much better if it was a saturated vapor. Okay? So let's write down this problem. Let's write down this problem and we're going to fix the cycle. So problems with reversed Rankine cycle. Problems. The big problem is, number 1, compressors can't or can be damaged by liquid in vapor liquid mixture. Okay? If we have liquid in the intake for the compression process, we got a liquid over here. Whoops. We got a little bit of liquid here in the compressor intake or the beginning of the compression process. That is going to cause damage to our compressor. Okay? So the solution is to make sure that state 1 is a saturated vapor. Okay? So state 1 will be a saturated vapor. Let me draw the resulting TS diagram here. Once we make these fixes, TS. So here's our saturation dome. I'm going to move this over. In fact, I'm going to draw the device and the TS diagram for our new ideal refrigeration cycle. So we have the TS diagram over here. TS. Here's the dome. Here's our, let's see here. Here's our evaporator pressure, or P min. And here's our condenser pressure, P max. So we're going to change state 1 to a saturated vapor. Okay, state 1 is a saturated vapor. So let me draw a compressor here. So we're doing some W dot compressor. So state 1 of the working fluid is a saturated vapor at P min. Okay? Okay, so now we're going to compress it. Let's do it reversibly. This is going to be an ideal. So this is going to be an ideal cycle. So I'm going to compress it isentropically because it's reversible and adiabatic. So we end up at state 2. State 2. So at state 2, we have a superheated vapor. Okay? Superheated vapor at state 2 out of the compressor. So this is the compressor. Compressor. Then we are going to reject heat all the way down to a saturated liquid. Actually, let me check this and make sure. I want to make sure that state is correct for the ideal cycle. I don't want to give you some improper information here. Yes. Okay. So let's reject heat in a condenser. So Q condenser. So let's reject heat and call this state 3. State 3 is a saturated liquid. So we're going to reject heat, Q dot condenser. So this is a condenser. Okay. There's state 3. So this is a saturated liquid. Okay. Now, what's the other problem with the reversed Rankine cycle? Number 2, if you recall from the problem that we did involving a Rankine cycle, the specific work for the pump was much, much less than the specific work for the turbine. What that implies is, for this reverse device, the specific work for the reversed pump is still much, much less than the specific work for the compressor. Remember? The turbine became a compressor, and the pump became a reverse pump, or a work-producing device. A work-producing device. So since the reverse pump produces so little power, remember W net will be W compressor minus the energy recovered by the reverse pump. The reverse pump is a work-producing device, the compressor is a work-consuming device, and the net power to run the cycle will be the difference between the two. Because the reverse pump produces so little power, let's just get rid of it. It's just an extra expense. Let's not put a reversed pump device in there to extract a little bit of energy from the flow. It doesn't make any difference. It's so small. It's just an extra expense, an extra piece to go wrong. So let's replace, so eliminate reverse pump. reverse pump and replace with a throttle. Remember, we did an example. We talked about a throttle. I think we did an example maybe a month ago on a throttle. Throttle is a restrictor that opens up and allows for a pressure drop. Okay? So instead of having this pump here, I have a throttle. So a throttle is a restrictor of some kind. The symbol used for a throttle, I'm just going to put a little box here. So this is a throttle. Throttle. And so you get a pressure drop across the throttle. So this is state 3, this is state 4. So right here at state 3, I have a P max, and then I drop all the way down to P min. It's just a little restrictor. It's just a little restrictor. Just a little restrictor. Okay? And then, so now how does a TS diagram look with this throttle in there? What's going on? What's the relationship between state 3 and state 4? Let's take a moment to analyze a throttle here. What does a throttle do? How does it work? So we're replacing this pump, reverse pump, with a throttle. What is a throttle again? How does it work? What does it do? So throttle, what is a throttle? What is a throttle? Well, a throttle, and again, I think we did an example, is a restriction followed by an expansion. It's a restriction in the flow or a pipe followed by an expansion. So here's our control volume. So mass flow comes in at, in our case, location 3. So we have an m dot, and then mass flows out, m dot, and we end up with state 4, according to our diagram there, okay? Now let's say this throttle is adiabatic. Let's say it's insulated. Let's say it's insulated. So if I apply the energy balance to this thing, it's an open system, single inlet, single outlet. You see any wires in here, any turbines, any boundary work going on? Nope, nope, there's no work going on, no heat transfer. If we neglect kinetic and potential energy changes, simple application of the E balance gives 0 is equal to m dot H out minus H in, which is H3. The m dots will be the same going in and out. Okay? In other words, this is an isenthalpic device. H4 equals H3. So it is isenthalpic. Enthalpy, isenthalpic. Isenthalpic device. Enthalpy is conserved across a throttle. Now let me point out here that the pressure, this is the high pressure side, so this is the P3, which is P max. And this is P4, which is P min. Is this process, as the flow moves through here, is that reversible or irreversible? What are the 3 irreversible processes we've been talking about? Heat transfer across the finite temperature differences, process involving friction, and unrestrained expansion. We have flow going from a high pressure to a low pressure and nothing else is going on. That is an irreversible process. So the S balance, there's no heat transfer. So the S balance says 0 equals m dot S4 minus S3 plus, minus S dot gen. okay, minus S dot gen. Now this is irreversible, so this is positive because we have an irreversible expansion in the throttle. So this implies that S4, specific entropy at the outlet has got to be greater than specific entropy at the input. So entropy goes up as pressure and temperature fall in this throttle. Okay? So the expansion process in the throttle looks something like this. Entropy goes up. So this is delta S from 3 to 4. Entropy goes up. Temperature and pressure fall. Enthalpy is the same. So note H3 and H4 are the same. So H3 is equal to H4. And then we have the heat addition here in our evaporator. So 4 back to 1. So we have Q dot evap. Evaporator heat addition. So this is where our heat, Q evap. This is where our heat goes in. You can see here that if we have a saturated liquid at the maximum pressure, the fluid, working fluid going into the evaporator will be a mixture of vapor and liquid. So it's going to have some quality at state 4. All right? So this is the ideal refrigeration, compression refrigeration device. It's basically a modified Rankin device, Rankin cycle, where we've taken out the pump and replaced it with a throttle. And we've made the compressor inlet state, a saturated vapor, okay? Now there are all sorts of deviations away from the ideal cycle. So there are all sorts of things that can happen to make this thing non-ideal. Let's just go over some possible variations on the refrigeration cycle from the ideal cycle. Of course, the obvious one is having isentropic efficiency for the compressor being different than 1. So having irreversibilities in the compressor. So here's an example of a non-ideal cycle, non-ideal refrigeration cycle. So we could have a whole number of things happen. So this is TS. Here's the dome. So here's our P min right here. Okay. So we could have, for example, state 1 being a slightly heated, superheated vapor. So we could have state 1 right here. Maybe. We could have non-isentropic compression up to P max. So this is state 1, this is state 2, this is 2 sub S. So we could have non-ideal compression up to state 2. Fine. We could have a pressure drop in the what? In the condenser. So the condenser is like a radiator, it's a heat exchanger where the fluid is turning from a superheated vapor into some kind of a liquid. So we could end up at some lower pressure. So we could have P condenser outlet. We could have a pressure drop in the condenser due to friction. And so state 3 might look something like this. So we could have isentropic efficiencies of the compressor less than 1. We could have a delta P across the condenser. So this could not be equal to 0. We could have a pressure drop across the condenser due to friction. Then, of course, we have the expansion in the throttle. Now, maybe we also have a pressure drop across the evaporator. So here is my here's my condenser inlet pressure at state 4. Sorry, evaporator inlet state at state 4. And then we could have a pressure drop. We could have a pressure drop, just like in the condenser. We could have a pressure drop in the evaporator as well. So delta P evap could also not be 0. Of course, recall, so the other one was state 1 or compressor inlet. Could be a superheated vapor. That's a deviation away from ideal behavior. Also, it's hard to see, but the throttle inlet could be a supercooled liquid. So throttle inlet could be a supercooled liquid, SCL. Okay, so those are all possible deviations away from the ideal cycle. So the ideal cycle, again, is compressor inlet, saturated vapor, isentropic compression up to a superheated vapor, isobaric expansion down to a saturated liquid, throttling, and then we have isobaric heat addition in the evaporator. That's the ideal cycle. And of course, these things are all open to deviation away in the real world. We could have a superheated vapor at the inlet state for the compressor. We could have non-isentropic operation for the compressor due to irreversibility. We could have a pressure drop. We could have a pressure drop in the condenser. We could have a supercooled liquid for the inlet state for the throttle, and we could have a pressure drop across the evaporator. These are all things that are deviation away from ideal behavior, okay? Okay, let's break this for a second. We'll do an example.